Hello again from the forest. Come check this out. All right, so I have two test tubes of liquid here. We need a little food coloring in those to do what we're gonna do with them. So there's some food coloring for that one. And kind of cool to see that green spread down there, and a little food coloring for this one. And wait a minute, that was kind of different, right? Did you notice how the food coloring went right in at the top of this one and spread all the way down? But for the second one, it kind of skipped the first part there. What could have caused that? Well, you may have guessed that this test tube actually contains two different liquids. So the first test tube, that was just some ordinary water, and as you know, food coloring will mix nicely with water and turn it green if it's green food coloring. This test tube had some hexane in it along with the water, and those hexane and water liquids are sitting in two different layers here. The food coloring skips the hexane layer entirely and goes down to the water layer. So why is that? Why don't the hexane and the water combine? Some people like to say that that's density, and density is playing a role here. The difference in density is why the hexane is sitting on top of the water as opposed to underneath the water, but it's not why the two of those are not mixing. So what is it? Well, there's an expression you're probably familiar with. Something and something don't mix. What is that? Oil and water. Oil and water don't mix. Hexane isn't exactly oil, but hexane has properties that are similar to oils. I will show you a bit about the structure of hexane in just a second, but before I do that, to demonstrate that it's not just a difference in density that's keeping those things from mixing, let me show you something that is also less dense than water, but will mix with the water. This is some ethyl alcohol. Ethyl alcohol is less dense than water, and I'm gonna try to pour this in very carefully so that it doesn't thoroughly mix with the water and it sits on the top of the water. So let me pour this. And so you can see that the food coloring does mix in with ethyl alcohol. Ooh, that's more of that than I intended to pour. It mixes a little bit with the ethyl alcohol right at first, but we still got a layer of ethyl alcohol up on the top there. So how is that any different than the hexane then? Well, let me show you this. If I take this hexane, I put a stopper on the top, and I shake it up, I can get those liquids to mix together temporarily, but as you see, they separate back out. The hexane just wants nothing to do with the water, or we could think of it actually as the water wanting nothing to do with the hexane. But in any event, those two things separate, the food coloring stays with the water. If I try that same thing with this ethyl alcohol and water mixture, once again, you can see I'm separated here for now, but when I shake them together, we're getting that green now mixing more throughout the liquid, and we don't get a separation out of the ethyl alcohol. There's still a little bit of a color gradient because the food coloring kind of went to the bottom there, but I can turn that over, maybe that does better than shaking, and get those things really thoroughly mixed together despite their different densities. I try that with the hexane, turn it over, hexane goes to the top. Turn it back over, hexane goes to the top, doesn't mix with the water, doesn't take on any of the food coloring. Okay, so why is that? Well, it all has to do with intermolecular attractions. Let's come over here. Water, as you know, is a polar molecule. It also forms those nice strong hydrogen bonds between water molecules and can also do London dispersion forces, as all molecules do. But dipole-dipole attractions, hydrogen bonds, good strong connections between water molecules in the liquid phase. Hexane, on the other hand, has this chain carbon structure surrounded by hydrogens. There's no positive or negative end to this molecule, as those small, slightly polar bonds go all different directions. And so this is a non-polar molecule. And the basic principle in mixing of liquids, like we were seeing, is that like dissolves like. Things that have similar intermolecular attractions mix well together. Things that don't have similar intermolecular attractions don't mix well together. So hexane and water, like oil and water, don't mix. Why is it that similar intermolecular attractions are required for mixing? Well, we can see a model of that over here with my stir bar and chalk molecules. So let's consider for a minute some molecules that attract each other strongly, like these stir bars. I take those molecules and I'm going to spread those in my tray. I'm going to take some more stir bars that I have marked with green and put those in my tray. And I put them and I shake them all together and give them some random energy, and look at those things. They just attract each other nicely, and the green ones and the white ones are all mixed together there. Similarly, if I take my nonpolar molecules, so my pieces of chalk, no attractions between them or very weak attractions between them, and spread those around, and take my green colored chalks and spread them around and give them that random kinetic energy, and you can see there's absolutely nothing preventing the white ones and the green ones from mixing together. So we've got a mixing of the different kinds of nonpolar molecules there. On the other hand, if I take some of those polar molecules and some of the nonpolar molecules, it doesn't really matter which one I use, and I put them all together, even if I start with them mixed up like this, once I shake them around and give them that random energy, you can see that the polar ones all clump together there to the exclusion of the nonpolar ones. So that's what's going on. We have things that attract each other strongly. If you try to mix in a molecule that doesn't attract strongly and doesn't have the ability to attract these other molecules strongly, then it won't be able to mix in, and we end up with two separate regions in our liquid, two separate layers in the case of what we had with the hexane and the water. All right, so one last thing to try over here. I have here a bottle of elemental iodine. I'm going to add this iodine to my hexane and water tube, and I want you to think about what's going to happen when I put iodine in there. If you need to, pause the video, take a moment and remind yourself of what the structure of iodine would be. So once again, elemental iodine, we used this back on the very first day of class. Did a reaction where some of that stuff got vaporized and made a purple cloud. And iodine, a solid under ordinary conditions, we'll see how it mixes with our hexane and water tube. All right, so I'm going to drop this in here. And where does the iodine go? Well, if you have a sharp eye and my video was high def enough, you might see that the iodine, some of it is kind of stuck on the surface of the water layer. Some of it may have sunk all the way to the bottom of the water layer because that solid, yeah, there it is, I see some on the bottom. That solid is more dense than anything in here, and so it goes to the bottom. But as you also may notice by the discoloration of the hexane there, some of that iodine dissolved in the hexane on the way down. Is iodine dissolving in the water, do you think? Let me shake this tube up a little bit. So when I shake that tube up a little bit and the layers separate out again, notice the difference in the hexane layer. What's happened to that? All right, so clearly that's more purple than it was before. What do you think more purple indicates? That is more iodine has dissolved in the hexane layer. So still got some iodine in the bottom there, but iodine dissolves better in the hexane layer than it does in the water. That doesn't mean it doesn't dissolve in the water at all, but it has a very low solubility in the water. Those of you who are campers or backpackers may have used iodine tablets to purify water before. The iodine tablets that you dissolve in the water do dissolve in the water a little bit and disinfect it, but they do not have a very high solubility in water. But the iodine does dissolve nicely in the hexane there. The reason for that, well, intermolecular attractions. Iodine diatomic molecule, one bond, non-polar bond, because it's between the same atoms, so no difference in electronegativity. And so that's a non-polar molecule. And so once again, like dissolves like. The non-polar molecule mixes nicely with the non-polar hexane molecules, doesn't mix well with the polar water molecules. If you want to play around with any of that stuff at home, you probably have some oil, you probably have some water. You can set up something with different layers, and you may be able to make a few different layers of density if you try things like adding salt to the water, or find something that can dissolve in your oil to change the density of that a little bit, or maybe some different types of oil if you want to play around, like I don't know if you have some motor oil or something that you can work with there as well. But all of those things are related to difference in intermolecular attractions. So good to see you again, and we'll check you in later. Bye.